Questions for Mark before we move on to the panel? Okay. We've got Josh, who's going to start off with a presentation, and then he's going to move on to the panel. So I'll just turn it over to you.
All right. Hey, Woody, where are you? I needed your help still. Is he here? Woody? I guess he's not here. All right, all the panelists, come on up for the power panel. Go ahead and sit up here. What I'm going to do, everybody, is a little Google Earth presentation, flying around Colo in the US, and then some slides sort of setting the standard of what we're going to talk about. A lot of these are just my opinion, so the panelists are going to dispute it, and that'll be fun. That's what it's all about. Yeah, come on. You want John up from CRD? Who's still going to come on? John from CRD? Yeah, yeah. Hi, how you doing? All right, this is why I needed Woody to change the resolution. Anybody know how to change the resolution on Apple to help me out with this thing so I can actually do a cool presentation? Here he comes. Good. I'm rescued.
What would you like?
Whatever worked good for all these guys. I'm going to probably handle this.
Think any further, we're probably going to go beyond the projector's resolution.
The one is small enough so everybody can see everything as it flies. So everything's...
Let's do this.
Everybody excited yet?
Where's your dock?
Right down the bottom. Drop down. If you got to get rid of this, click on that. And I'll get that dock here.
Okay, so there's the resize tabby.
Did you switch screens over? That's what I get for not testing this first, so everybody bear with me a little bit. Sorry about this.
There you go.
Okay, guys. I've always wanted to do this in front of a larger crowd. I've done it a couple times now over in Europe. This is a little Google Earth flyover of Colo in the US. These are large telecom hotels. Some are full, some aren't. Some are voice, some are IP. We're going to fly around the country. It takes just a few minutes, and I'll talk to it as we go. I'm not covering every building. It's not all-inclusive. If you're a data center operator, don't get offended. Don't whine. It's just a few things in here, so just to make it interesting for everybody. And this sets the tone where data centers sit. All of this will fall into cooling, power, green data centers, why it does or doesn't work, and where we're going to go with all this stuff. Whoops. That's okay. All right, guys, this is where we are now in San Jose, in case you guys didn't know where you were. And now we're going to fly into New York. This is 111 8th, which is the IP hub in New York. Very big building, about 1.5 million square feet or so. It's got a hospital in the middle of it. Google has offices there and a lot of data centers. Lots of cooling on the roof. You can see how hard it is in a downtown environment to squeeze all this hardware on the roof on both sides. It's absolute mayhem to get anything done there. It's unions, everything you wouldn't want to deal with in New York. Then you got 60 Hudson. This is more of a long lines transport, voice building. Same kind of situation. Lots of stuff on the roof. You got fiber conduits running up a flower shop in there. Very exciting. Now, I'm not showing everything in New York. I know there's a lot more buildings. The next one is 32 Avenue of the Americas. Again, voice and IP building. Most of these other facilities are getting very full, so people are filling these things up quickly. You can see all the infrastructure on the roof again. I love doing this, by the way. This is fun. 165 Halsey. This is where you used to have to get shot when you went to the colo, but now it's gotten much better. New Jersey is now a nice place. You can see all the infrastructure on the roof. I'm going to fly around and make everybody nauseous. This is Switch and Data's new facility in New Jersey. Very nice site. Interesting factor, they went right next to where all the power was. Isn't that smart? And right next to the railroad where all the fiber is. That's smart too. But it's a very big site, big step up for what Switch and Data is doing now, a different model. Equinix Secaucus is one of the nicest colos I've ever been to. I give them big compliments on this. It's a great site. You can see all the power, cooling, very well built. And you'll notice they got really smart and did it next to the railroad. That's where all the fiber is. You'll find the same thing happening with all these colos if you go around on the tour. It makes it interesting. Equinix Ashburn. Most of these buildings are now Equinix Ashburn. It's absolutely huge. It is the place to be in the DC area. I think this was A, so I might be right or wrong. Nobody helped me on this, so that's A, okay. You can see they're right next to the airport. Which one is it? Yeah. Ah, okay, same thing. This is 350 Cermak in Chicago. You can actually see the colo. I put these little markers, I oversized them a little bit, next to the railroad, right next to the railroad station, as a matter of fact, big train station. And you'll see, we'll zoom into the cooling infrastructure on the roof there. And we'll go around to the power infrastructure. But again, you notice next to the railroad, lots of fiber. These buildings are pretty full. The newest big building to come online in Chicago is Equinix's new site there. I don't know what you guys call it, but again, what's interesting about this, it's next to the railroad, right next to the airport, lots of easy access. All these factors are coming in play for people to build colo. And next to the railroad, as you can see, there's tracks right there. There's all your fiber coming in. So this is how you do all these placement to build these colos. Everybody sick yet? We're going to Dallas. Isn't that exciting? This is InfoMart in Dallas, big glass cake-looking building. Equinix, Switch and Data, a bunch of other colos in there. Pretty full building again, a lot of capacity issues there. It was retrofitting a building to make it a colo, so it wasn't really intended to be that originally. Next to the railroad tracks, all the power and cooling infrastructure back there. You see all the tracks coming up to feed in the fiber, so that made sense. Forget where we're going now. I think we're going to Phoenix. Okay, Phoenix, isn't that exciting? Digital Realty Trust is a big, big building in Phoenix. There's certainly others, but this is the biggest. Huge building, lots of overhead infrastructure. And you'll see we'll fly out next and we'll go over to the railroad tracks. So you actually get to see where all the fiber comes in, pretty close to the building. Now I think we're going to Seattle. Nope, Los Angeles, got it wrong. One Wilshire. Another high-rise building, it says One Wilshire across it, so it's really easy to find. In case you wanted to know, all the infrastructure inside is on the roof or inside. Equinix has a big building right down the road. You can see all the generators and cooling overhead. Again, massive. And again, you're looking at downtown environments, very hard to scale. This is where it sits. Another Equinix site located in another part of LA. I'm now dizzy and lost, so I don't know where I am, but lots of generators and cooling there as well. And again, near some tracks. I'm guessing that's where the fiber comes in. This is, again, just my opinion. And now we're in Weston. You're looking at the Weston building in Seattle. Again, a high-rise office building retrofitted to handle all this stuff. You'll see cooling infrastructure on the roof of the garage and power and everything else, trying to squeeze everything in there. And again, big hassles right in downtown Seattle. Where do we go now? Good God, Silicon Valley. So you're going to see a few buildings here. 365 Main. It's going to be the first one we're going to. Again, a huge building, and a lot of this came out of the dot-com era, when everything was, or dot-bomb era, I should say. This building is full. You'll see we'll go to 200 Paul next, and that building is full. Again, another building. You notice generators, cooling, everything overhead, squeezed into a downtown environment. So it's critical to understand how this infrastructure gets placed inside these downtown environments and where data centers are going in the future. Again, next to the tracks, you have good fiber access. When we get down valley, you're going to see some pretty cool things because of Silicon Valley Power. They've got these turbines right in the middle of the city. Makes it very interesting. Pax Palo Alto, in case anybody hasn't been there, kind of close. Walgreens burnt down? Yeah, I got old Google Earth stuff. What can I do? Blame the Google guys. So now what we're going to do is actually fly into the Down Valley area. Uh-oh. There we go. So Switch and Data's got a big new site there. This is Terramark's sites at 3030 Corvin, right off of near Kiefer Road, and we're building a big new building there. Everybody's building new stuff. Again, all in Silicon Valley Power. Slide into the next one is going to be, this is Equinix's Lundy site, and I really like these sites for very smart placement. You've got a building and a lot next door where you can build more stuff. Isn't that smart? So now, instead of in a valley area where you have really tight space constraints on land, you're able to actually build something next door. So that's a very good play there again. You'll see the same thing at 11 Great Oaks. You've got an Equinix site and you've got empty land next door. So again, a very smart thing. Now let's slide into the land as we go to the next one. Isn't that pretty land? All right, here's where it gets really interesting. This is in the Space Park area, and you've got Equinix, you've got Digital Realty Trust, you've got a couple of DRT buildings there. Yahoo's got stuff there, a lot of other folks, and if you notice right there, you've got a power plant with turbines right in the middle of it, right next door to you with all the fiber sitting there. And again, being very close to the airport. Again, all your infrastructure, those sitting on the roof and squeeze in. All these centers are getting pretty full. So if you got colo here, it's full or getting full, or it's not full, but you've used all your power. Now we're in Atlanta, 56 Marietta. This is actually a telex building. And look how the infrastructure is stuffed on every little inch of space. That building is just maxed out. Again, hard to get new power and cooling in places like that. And now we're going to my place down in Miami, Napa of the Americas. Kind of a cool one because of the way how we get district cooling in place. And all the overhead infrastructure, again, inside that building. And all of that has to be protected from Category 5 hurricanes, so a whole different animal. District cooling plant to actually cool it, so it's cooled from a building a few blocks away, providing 7,000 tons of chilled water into it. And again, a downtown environment with all the railroads coming in, same form factors to get all that stuff in place. And we're back again. Wasn't that cool, guys? I always wanted to do that in front of a crowd. You guys are my guinea pigs. All right, guys, I'm going to slide into a PowerPoint presentation and kind of lead into the conversations we're going to have with the panelists now. Okay. So data center power trends, a NANOG 42 power panel. This is a panelist, a very esteemed panelist actually. You guys, congratulate yourselves, good. So these guys are all going to talk about different issues we're going to face, having data center cooling, power, technology issues, and green. Does it make sense or not? Which I sort of think it doesn't in the big data centers from a big picture standpoint. We'll go through that. So let's talk about some of the issues here. A 1 megawatt data center takes 177 million kilowatt hours, worth over $17 million over its 10-year lifespan. These are all analysts' opinions. I'm just repeating them. By 2008, 50% of today's data centers will have insufficient power and cooling. Isn't that scary? It's 2008. Anybody realize that? So that's today, right now. We don't have enough cooling or power, and that's in a lot of data centers. By 2010, half all enterprise data centers will have to relocate or outsource applications to another facility. The reason I think that's important to all of you guys in here, because most of your ISPs and networks and things like your content guys, if those enterprises take up all that data center space, you now have no room for your routers and your servers. And that is what's happening at this moment. Hosting, outsourcing, everything. The economy crushing, they're all moving into data centers and outsourcing and getting rid of staff. So it's going to take up that same space it takes 2 years to build. And this is a fun factor. We created 161 exabytes of data in 2006. I don't know what we've done this year, but with video and everything else, it's getting monstrous. So what happened? So the US colo market was swamped with space after the dot-com bomb. Everybody remember the Valley? Every building was empty. All the parking lots were empty. It was a nightmare, and all these colos are being sold for nothing. Well, those all got gobbled up, and those actually picked up for pennies on the dollar and then filled up. So 7 million square feet of data center space built out at 100 watts a square foot, which is useless today because 100 watts a square foot is a Band-Aid on a big giant wound. It just can't handle it today. So it's all gone, so now what's going to happen? So that what and no offense to anybody, I call them penny on the dollar companies because they're the ones who acquired the penny on the dollar data centers. The Digital Realty Trust, 365 Main, CRG, DuPont Fabros are now building data centers 100,000 square feet and larger. These big giant data centers with really high power. Now what's happening is you've got these guys doing metered power. So you have more traditional colos like mine, Terramark, or Equinix, or Switch and Data. We don't really do metered power. We provide what we consider higher end service and don't do that, but these guys are doing that. Big offset and a problem for us. So it puts a lot of market pressures on what's happening in these things, yet it's still very expensive to build these things. You've got the NE2 free IX, which we'll talk about a little bit, Telex, some exciting things going on, but what happens, it creates a war. So you get a pricing and business war, yet we're all running out of colo, so then you start getting a space crunch. So now what happened? All the new data centers are 200 to 400 watts a square foot, and that is an exponential increase in the cost to actually build these things and get these going, and everybody will be able to talk about that on the panel and how difficult that is. If you actually want to deal with these combating these power cost issues, and you're a big company like Google or Yahoo, you're going up to Quincy, Washington, or the Dalles in Oregon, and buying 2 cents a kilowatt hour, or who knows? I'm only taking a guess at that because I don't know what they've negotiated, and actually buying hydropower. So pricing now is all over the place. You got some old data centers that are carrier center at 50 or 70 or 100 watts a square foot. They're $400 a rack. So what? Because you can't even put any servers in it anyway. Put 2 servers in it for $400 a rack, knock yourself out. Or you go to 1,500 a rack for a higher-end data center and fill it up most of the way, maybe, depending on what you're trying to put in there. If it's blades, it's more of a problem. So now all of the newer colo sites are starting to raise prices because we all have to pay for these really expensive infrastructure. It includes more cooling, more power, more feeds, more commitments to the utilities. PG&E isn't going to give us 100 megawatts because we say we need it. They're going to make us financially commit to actually paying for some of that to make it happen. They'll agree with it. And it used to be the public service commissions, if you wanted 100 megawatts of power and you told them that, they would have to deliver it. And if you didn't use it, oh well. But now it's a little different story. They've gone back to those PSCs and changed that story. So this is an interesting slide I've been using for a couple of years, but I really like that we're in 2008 again, and it's at 35 million servers inside these data centers. And if you're going to tell me there's enough data center space to actually accommodate all this stuff, you're nuts, because it's not there. We've got a big, big problem. No matter what comes on market, it's going to get filled up. The content's going to fill it up. The enterprises are going to fill it up. It's going to be a big dilemma, and it's coming. And here's the biggest issue. They're much hotter. So the old servers you had in 2000 were nothing. Now in 2007, 2008, they're blades, they're running sometimes 20 kilowatts a rack, you got big empty space around them. It becomes a heating and cooling nightmare trying to be able to deal with all this stuff. We can always deliver the power load into it, but actually cooling it is much harder. This actually shows some of the trend of growth. Martin was going to talk to this slide. Just stand up.
So there's a couple of different things going on. Your data centers are not just full of one type of equipment. There's servers, there's networking equipment, there's storage. If you listen to what Mark talked about earlier, there's even storage that turns itself off and saves power. So all of that has trended slightly differently over the years. But what has happened is that the amount of usage of each one of these items has also changed. When you look at the amount of content, you look at the amount of servers, you look at the amount of services that are delivered on the internet, that has increased dramatically. Yet the number of routers and switches, although it's increased and its usage of power has increased, the actual numbers have not increased. Hit that one. Well, you can talk about it.
I'll talk about this from a data center perspective. I operate a 750,000 square foot center in Miami. My issues, I have huge amounts of power coming in, but all that power going in is actually dealing with my infrastructure, not really necessarily going to the hardware. I think Mark did a slide that showed about 53% is actually going into hardware. That it's arguable depending on the center, but the problems you have in a carrier-neutral co-location is from where Sprint's going to have a bunch of GSRs or CRS-1s in one cage. Right next door to them, I've got CBS television with 80 racks of servers blasting out heat without blanks in them, and I've got to hassle them constantly to deal with that. Right next door to them, I got Akamai at 384 watts a square foot, just below dryer, and then I got another carrier, then I got an undersea cable guy, then I've got some guy with like 2 racks in a big empty cage. How do I manage all that? It's just an absolute disaster. So when you operate your own data center, you can get to those tighter efficiencies. When you have a carrier-neutral center with a bunch of different customers, it really just got to do it with brute force air or liquid is where it's probably all going to go. Martin, it's yours?
Yeah. So a couple of other things have happened. In the purest world, in the purest data center, which is normally in the enterprise space where things are pretty unique, people have gone out and actually measured this. This is a report out of this is a graph out of EYP that basically shows around 50% of the power used by the actual IT equipment inside an average data center. This is very similar to the graph that Mark showed, whether the number's 50 or 53% or whatever. This is sort of a fairly easy to manage, not the type of data center that Josh was talking about. But what's interesting to note about this is that people have started to understand how to measure this. And one of the measurements that came out before the Green Grid, which is an organization, if you've not heard of it, the Green Grid, type it into your favorite search engine, have a look at there's some good white papers to read. But they're starting to promote a couple of different ways of measuring efficiency in data center, because it's pretty impossible to know which one's which. There's a button in front of my microphone. Operator error, I could have used it. Anyway, in the PUE world, what you're doing is you're measuring the total amount of power. You're measuring the whole pie, and then dividing that by the amount of power that's in use by the IT equipment. IT equipment in this case could be networking equipment, storage, whatever. It's not the cooling. It's not the electricity that's lost from the transformers when you're stepping down voltage, et cetera, et cetera. But keep in mind, you look at this graph, this one says 3%. There's an APC graph says about 2 or 1.5%. That's the lighting. Turn the lights off. If you're running an unmanned data center, turn the lights off. When you start getting out to buildings that are running in the multi-megawatt range, 3% of that can actually relate to real money at the end of the year. So this is a report that came out from Tier 1 middle of last year, which simply talks about in the data center internet infrastructure data centers, that's not in enterprise, the amount of utilization, the amount of space that's available. That number has grown from 2002 in the 25 to 30% range all the way up to today at the 50 to 55% range. That's the utilization. But what's happened parallel to that is that what goes into those data centers has also increased. The multiplier here is that the power usage. I went back and looked at what type of equipment was being put into data centers in 2002, and if you're pretty ahead of the curve, then you're starting to put in HP blade servers or equivalent blade servers, but they're running with P3 processors. The cooling technology inside them wasn't really brilliant. So in fact, actually, there was a few people using transmitter chips or even laptop chips at that level. You look at today, or even a year ago and then today, and you're starting to see 1U and 2U Dell servers. You're obviously seeing blade servers that are very high density. Look at the 10U blade server from Sun. The basic power utilization, once you've bolted every blade in there, is about 5.5 kilowatts in a 10U space. And that's a dramatic difference than a 600 watt for a whole chassis in 2002. So not only has your data center space been increasing, the actual numbers of the amount of space, the amount of power you're using has also increased. Finally, I did another quick analysis. I went back and looked at 8-9 years worth of Tier 1 articles about power, and I found two interesting trends. Obviously, the trend for higher powered data centers going out there, but also a little bit of truth in advertising came along with that as well. What people were claiming they could do 5, 6, 7 years ago really was just unsubstantiated claims. What's happening now is that people are coming into data centers and really trying to make sure that if you're advertising 150 or 200 watts per square foot, you can really do that over the whole size, the whole cage, the whole space that's provided. Whereas prior to that, you can actually go and look back at the presentations from colo companies that said, oh, we can do 200 watts per square foot, but we're going to leave a big space around you. And that really, from the data center total power point of view, really wasn't the type of document. But I'm just a couple of examples here. The switch and data site, which you showed on the map, is now built up to 200 foot or higher, 200 watts per square foot or higher. You're seeing people announcing up to 300, 350, and a few people saying, hey, you know, we can do more than that. There's companies that are doing separated hot and cold aisle, which are starting to do even higher densities than that. So the story has changed over the years, but it's definitely becoming more mainstream.
So now we get into cost of building something like this. A 20,000 square foot tier 1 or tier 2 data center. So we'll call it kind of your ghetto colo, one that's just going to work. It might or might not work after an earthquake or a storm or something like that. You kind of don't care. You're a spammer, or your just content doesn't matter, or you're broke, or whatever it may be. But there you have it. That's 15.4 million. Right? That's a lot of money. Now, that's not if you picked it up on the market after, pennies on the dollar or somebody went bankrupt. This is truly building it. An existing warehouse, let's say. 20,000 square feet of tier 4 data center that's going to be up no matter what. That's 5 nines or even 100% SLAs. That's N plus 1 plus 1 or 2N plus 1 or 4N or whatever you want to make it. Really high-end redundancy from the Uptime Institute standards. 48.4 million for 20,000 square feet. That's a big difference, isn't it, guys? So now the lead time to build a 200 watt per square foot data center, 75,000 square feet, is about a year. It's going to take a year to build that building. You got to order generators, you got to get PDUs, you got to do ground up construction, you have to do design development work, you have to get permitting, you have to, claim you're going to give everybody 1,000 jobs and probably only provide 20 because it's a data center. Remember, there's no people in there. You're going to have to actually try and get all your incentives together, make all this happen. Now, the biggest issue is that if the IXs can't get the space built fast enough, then ISPs and content companies can't deploy, or the enterprises come in and do that. And that actually will start to cause a bottleneck in the internet. It's been seen in certain markets around the world where it's actually squeeze traffic down. Lack of available colo for the routers and the switches and the servers starts to squeeze the traffic. So the question is, are we actually going to do it enough, and is it going to be the right amount of power? So a large colo could actually have $2 billion of hardware on site, and that's quite literal. Or the amount of commerce that goes through it. It's certain sites in the US and Europe, it's immeasurable. I mean, it's really immeasurable. It can take off a whole continent. You got big sites like Google's data center up in the Dalles in Oregon. They're pods, 68,680 square foot per pod. They're really high power, but they're paying maybe 2 cents a kilowatt hour. Now, everybody's going up in that area if you're that kind of a content company, because the fiber doesn't really matter at that point. You just care about power costs. This is, I don't have a better picture. Martin and I were looking for it, we couldn't find it. Microsoft's Quincy site, 470,000 square feet, 47 megawatts. And I'm guessing at this stuff. It's so hard to find this information and try and find the real story of what it really is, but that's what we've worked out. Got Yahoo and Wenatchee, I hope I'm saying that right, in Quincy, 2 million square feet. I mean, that's huge. Now, this, of course, is going to be the Microsoft data center soon, right? I shouldn't say that. You got my building, 750,000 square feet, and at full build-out would be 100 megawatts. And it's insane. That's a city in a building. So cooling issues become huge. I'm not tapping myself on the shoulder. It's a really cool thing we're doing up in Virginia. 55 generators and a possible turbine site with one building actually be 80 megawatts and 100,000 square feet. That is 800 watts a square foot. Now start working out those costs from the numbers I showed you before. Absolutely insane. So now green energy. Does that make any sense? You see a Stirling engine here. That big wind turbine, that's a 3 megawatt wind turbine. One wind turbine. About a year and a half lead time right now because they're hard as heck to get. You can't even get installers to put them in. Oh, and then you need thousands of acres to actually put that in place. And then, wait, the wind doesn't blow. What happens? You got a problem. No power. So you got wave generation. That's really cool too, but I'm not going to power my 100 megawatt data center with a big tube floating out and hope there's waves that day. It just doesn't work. I'm a surfer. I like that stuff, but you know. The solar tower, these things are being done in Seville, Spain. That's great in Seville. They have these mirrors focusing up and you can cook thousands of eggs on that thing. It's pretty interesting to generate electricity. It works well in the city of Seville where they're going to be powered by this, but for data centers, come on, it's just not quite there. You can see this wind farm down below. I mean, I personally, as a company, cannot go and afford to buy 80,000 acres and stick a bunch of wind farms up there. It's not going to happen. So we buy green power, maybe pay more for that. That's the option, but actually producing that for these big data centers, it's just not quite there. There's different technologies you can use, like flywheels instead of batteries, trying to increase efficiencies, trying to become greener so we don't produce batteries in the factories and trying to dispose of them later if they go bad. There's things like actually going off the grid. This is some cool stuff from United Technologies, which makes Sikorsky helicopters and carrier air conditioning. Kind of cool thing, 10 megawatts would be 200 microturbines, and you have an absorption chiller system actually generating the cooling out of that. You're actually off of the grid at this point, and you're actually generating your own electricity from natural gas using turbines. You could take 15% of these things offline to do maintenance. Everything's still operating. The bad part is you have two choices here. You either use the grid as your backup, which still requires them to build all that infrastructure for you, have it on standby and have a substation there, or you put in tons and tons of generators. Those generators run, you're still not being green, you still got a big issue with fuel and everything else. So, and then if you try to go to 80 megawatts, you're talking 60 to 80 medium-sized turbines, 40,000 tons of absorption cooling. I mean, you have to hedge natural gas futures. It really gets crazy in where we're going with this stuff. Anyway, guys, I wanted to lead that into it for the panel. We've got a great panel. Michael Patterson, Senior Thermal Architect and Digital Enterprise Group from Intel. God, I don't know how to pronounce your name. Supo Bapit, from Vice President Distinguished Engineer at Sun Microsystems. Martin Levy, Senior Analyst with Tier 1. You got me. Mark Bramfitt, who you just heard speak before from PG&E. Edmund, who's representing Equinix here today. And Chris Malater from Switch and Data. And I'm blanking on a name right now. John, I'm sorry, from CRG. Martin? Yeah. Should I take this off? No. Please don't. Okay. So, get to the end. I know, I want the last page. Never mind. Forget it. All right, so we've got a set of people and stop. No, I just want to go to the last page. Gee, that really hurt. Where's the last page? There we go. And we know who we're talking to. So, we went through a bunch of stuff with Josh, but what really comes down to it is the fine detail. It isn't as easy to do some of this stuff. Mark's already talked about what this is like from the power company's point of view. And in fact, within the various times that I've heard Mark talk, and I want to give him credit with this, or give PG&E credit. PG&E, I think, has pushed the envelope out of all the power companies in the US to try and do this.
Other people in other places, Virginia, I believe, has now put a program that's modeled based upon your point of view. That's the power company. This is the power company trying to basically say, please use less power. Oh no, they're really saying, please use the power more efficiently. But either way, it's a push from that direction. So I'm going to take this, and I've got various different people to talk to, so I'm going to go take it from the chip level upwards, not from the multi-megawatt, but from the maybe 50, 80, 100-watt device that's sitting on the motherboard. So I've got two different people who can talk about this from a different point of view. Michael can talk about it from Intel's point of view, although his expertise is in cooling, which is sort of interesting because that's the problem that's caused by those chips. And so both from Sun, who can talk about this from actually a bigger direction, because you can talk about it from the system level point of view. But Michael, I want to give you the microphone for a few minutes and just let you talk to us about what's happening at the lowest level on the chip side.
Thank you. The slides in here?
That one you wanted? No.
I mean, the other slide down.
No. You have the other?
Okay.
No, I'm going to get you just to talk.
Okay. Well, I'll just talk then. A lot's going on, obviously. Certainly at Intel, we recognize the challenges that are created by the capabilities that we build into the processors. In the one slide I had that I did want to show you is a mini case study. It showed in 2002 that there was, excuse me, a data center that had a cluster, a high-performance computing cluster. This cluster was on the top 500 list. So if you're familiar with the HPC world, the top 500 supercomputers in there are listed. And this was, I think, in the top 20, and if I remember right, it had 25 racks and 128 megawatts of power. No, wait, 128 kilowatts of power. Got my 1,000 wrong there. So 128 kilowatts power, 25 racks, and used up quite a bit of space in the data center. So that was in 2002. 2007, to show the progress, that same performance that used to be number 20 on the top 500 list could be had by a single rack with, I think, it wasn't even a full rack, so it wasn't even 40 servers. It could accomplish the same number of teraflops in just a single rack. That rack consumed 21 kilowatts, but just a single rack. So the issue that we see is that going from that 128 down to 21 kilowatts, the challenge now is how do you deal with the 21 kilowatts? In the past, when it was 5 or 6 kilowatts a rack, it was reasonably easy to do. But now the capabilities we've built into it, the progression on Moore's Law, bringing in the more powerful chips that use less power, we can get the densities up to the point where we're looking at single racks that are now on the top 500 list of high-performance computing. The one thing I think that it has done is we have commoditized the server, commoditized the IT equipment, and as we've commoditized it, we have uncommoditized the building. So that's, I think, the main challenge, is that it used to be you'd bring in the servers or you'd go buy a mainframe and it was all a big deal, and that part was the non-commodity part. And then you just put in a 12-inch raised floor and throw a bunch of cracks around the outside of the data center and you'd be done. The room was the commodity part, and unfortunately, I guess it's actually good news, but it does mean we have to shift our focus. Now we've commoditized the servers, we can bring those in, high density, very inexpensive, and then but what we've done is focused now on the facility. To get to these 21 kilowatt racks, it certainly takes a good bit of engineering. Certainly you can do it, but again, now focusing on that side of the equation is going to be the key. So to support that, as mentioned earlier, you guys have heard about the Green Grid and Climate Savers. Certainly encourage everybody to look at those both and understand what's going on in both those organizations, because they can bring a lot of best practices and a lot of standards that will help you in that challenge, both at the server level and at the room level.
So So I'm going to ask you one, and put you on the spot, just so we get this on sort of the right level. As much as we've got high-performance computing that has gone sky high with requirements on whether it be university or other data centers to build that, what's happened to the power of the actual CPU chip, the actual chip that your company produces? What's the total power a couple of years ago, today? Where's it going to go?
Okay, good question. The power was ramping up, and that ASHRAE chart that everybody saw, you know, with the increasing density. And then there was a knee in that chart. That knee was actually when us and one of our competitors decided to quit chasing performance and start chasing performance per watt. So the power of the CPU was going to just continue to go up out of control, and it got to the point where it was going to be too much power, too difficult to cool. We saw that we needed to shift gears and go performance per watt, so that has changed. At that peak, I think single core CPU might have been in the 130 watt range. Today we have kind of turned the corner, and you can still buy 130, 150 watt CPU if you want just the ultimate in performance, but most of them are in the 80 to 110 watts. And the reason we've been able to do that is going to multiple cores. You know, the real simple way to describe it is you have two people working on a job, and two people can only work, I mean, if they work half as hard or half the frequency, they can get the same job done. But two people working, the nice part about a core doing that with the reduced clock speed is that the power consumed is far less than half. And so we can maintain Moore's law. It's a deviation of Moore's law, but the performance base of the server, you know, keep that moving ahead by adding more cores and spreading out the workload and moving work into a lower frequency core, just more of them.
Okay. Thank you.
Anything else?
No, that'll do for you for the moment.
Thanks.
But I'm going to go up the level and now talk about the systems, because we talked about high performance computing taking, you know, anywhere from 4 to 5 kilowatts a rack to these days being in the 21 that you quoted kilowatts per rack. You just don't go out and bolt things together to pull that off. Sabbath, talk to us a bit about Sun and what it's doing in this space.
So thanks, Martin. Actually, there's a lot of activity and a lot of very interesting technology innovation going on in the server industry, which is surprising considering that everybody considers it a commodity product and a commodity industry. And if it is commodity, you would expect that, you know, it's the most efficient producers of the commodity that would end up becoming the dominant market share vendors. But it turns out that there's a lot of technology innovation that's happening at the system level as well in order to make the next generation of servers good citizens of the data center. And, you know, Mark talked about the fact that in his presentation that, you know, as part of one of PG&E's incentive programs, they had an incentive on energy efficient equipment, and the first partner they partnered with was Sun Microsystems. One of Sun's CMT chip multi-threading servers was part of the PG&E incentive program. As far as I can believe, Mark, that was probably the first ever known collaboration between a utility and a server vendor to put more energy efficient servers into data centers and you know, get the gains that way. What's happening in the server industry is that, just as Michael said, you know, in the microprocessor industry, the design criterion has changed from absolute raw performance to delivering performance per watt. The same thing's going to happen in the server industry. And, you know, the next set of servers you buy, you should not only ask your vendors for benchmarks on performance, how many transactions per second will it run on my favorite database, how many web HTTP packets per second will it process, et cetera. But you should also ask how much energy it will burn in doing it. And so optimizing the server design point for performance per watt is really what the game is all about in the next generation of servers in the data center. And you know, I'm seeing a lot of innovation happening in the space of better utilization of CPU capacity in the server, but it's not just the CPU that burns power in the server. It's also memory, it's also disk, it's also I/O, it's also fans, it's everything put together that burns power inside a server. Servers that, you know, your average typical building block server, 1 rack unit high, that you could have bought maybe, you know, 7, 8 years ago, you could have probably, you know, figured on a 250 watt power supply being inside that server. Today, the same 1 RU server that you would typically buy with, you know, quad-core designs from Intel and AMD and 8-core, 8-threaded designs from Sun, et cetera, those things can burn as much as a kilowatt in 1 rack unit high dimensional, you know, rack capacity. And so you put 30 or 40 of those in a rack, you're looking at a 40 kilowatt rack. And so, you know, really to make servers good citizens of the data center, it's all about building things that self-calibrate their power draw. You probably heard the oft-quoted statistic that, you know, the average IT shop will tell you that the utilization on their servers is pretty low. Some numbers that are quoted are like 10%, 15%, and it's that number that is driving the entire virtualization industry. And if, in fact, you had servers that knew how heavily or how lightly they were used, because most IT shops will always size their server farms for peak capacity. But most of the time, you don't actually operate at peak capacity. You size them for peak because that's what you get paid for. You maintain availability for what, you know, however, once a year or a few times a year you might have peak demand, but you size it for that level or that load because that's what you get paid for, to keep it up all the time. But on the other hand, if you keep it up all the time, at peak capacity, you're wasting energy, because if your average utilization is, in fact, 15, 20, 30%, the typical server power curve is such that at 15% utilization, the average server is still burning about, you know, 70% of its peak power. So you got lots of servers at 15% utilization, each burning 70% of its peak power, you're in trouble. And so you need to look for servers that implement intelligent self-calibration of energy draw, servers that recognize through smart firmware that you know, the utilization level is fluctuating. It was high during the day, but it's low at night. So I am going to scale back my energy draw because I am now in a period of low utilization. So those are the kinds of innovations that you'll see coming out in the server industry over time.
Don't go away, because I'm going to ask you a question about the systems level stuff. Mark mentioned it earlier, but he talked about 80+ power supplies, but really just touched on it to a small amount. In the system level, give us an idea. Sun went through a very large rebuild of its data centers. You got rid of a lot of old equipment. So throw a number out there. How much power could be wasted by systems that aren't the latest and greatest? And where was that big change in the systems that are shipped to the full subsystems that are shipped into the data centers, where the power supply made a big difference to the amount of power being used?
So a great question. Power supplies certainly do make a difference, because the older servers that you might still find out there in operation probably have power supplies that are in the 70% efficiency range. And power supply, what is a power supply? It's essentially a small transformer. It takes a voltage that comes in off of the PDU and then steps it down to a voltage that's needed on the motherboard. And most transformers, whether it's the big gigantic transformers that you see out in the mechanical utility yards, or whether it's UPSs in your data center, or even the power supplies inside the server, they have what's called an efficiency curve. And what that means is the less you use them, if you use them only at 50% of load, you're actually using them at a lower efficiency point than if you use them at a higher efficiency load. higher utilization, you'll have a higher efficiency. And so the new generation of servers are using power supplies that are 80 plus. In Sun's case, many of our power supplies in our newer products are actually 90 plus, and they show a much, much flatter and smoother and better efficiency curve than our older generation of servers. So as an example, a couple of our customers bought our chip multi-threading line of servers that are optimized for energy efficiency and performance per watt. They were able to replace with 2 rack units high worth of equipment a competitor's servers that delivered the same performance in about 14 rack units high worth of equipment. In other words, they replaced 7 older generation of servers with a single new generation server, thereby gaining space improvements, thereby gaining power improvements. They cut down their power draw by a factor of 80% or something absurd like that. They cut down their space requirements, and they cut down their dollars needed to obviously install and maintain and buy those servers. So it's just an example of what the new innovation can save you.
Great. Thank you very much. So we've now taken it through from the chip server side. I'm now going to just open it up for everybody, but the first question is going to go to the 3 guys that we've got on here that are from the data center. Josh has already spoken. We don't need to hear more from him. But I've got Chris from Switch and Data at the end there. I've got John from CRG West and Edmund from Equinix. But I'll hit the middle one first. John, you're up to your eyebrows in data centers, and you're up to your eyebrows in power issues. Grab a mic and talk to us about what you're doing with the customers, because this was the conversation about nice new servers and new technology. What's really happening in the data centers? What do you want to tell the people that are shipping equipment to you right now?
Well, first, let me kick back just a second and talk about a little bit about the theory, and I'd like to use a case study to present that thought. And the case study would be here in Milpitas, California, since it's proximity makes sense, and Mark is here from PG&E. We found a property in Milpitas that's a medium-sized property, not the biggest data center, not the smallest. It was left over from WorldCom. It was originally designed as a DMS 250-300 site, about 70 watts a square foot originally. We picked up the property, and obviously the mechanical electrical component was not going to be anywhere near adequate to meet the needs of somewhere north of 200 watts a square foot. So how did we go about looking at that site? We knew that Silicon Valley and PG&E was, a great place to start with a new concept of how to build out a data center first, to meet the mechanical electrical requirement of bringing that up to 200 watts a square foot or more. So we had a meeting together with Pacific Gas and Electric. We had Carrier, who we had selected for our chilled water and cooling systems, Caterpillar, who was going to provide us our generators, and in fact the city of Milpitas to make sure that they were aware of how we were building out the sites. And as a group, we sat down in a room for about 3 days and beat out a data center design that would bring together the best practices of both bringing the utility power into the site as well as how we would best transform that down to usable voltages and currents and distribute it throughout the facility, and even more important, extract the heat from the building in a closed-loop chilled water system that would not harm the environment. And in addition to that, the generators were built at what we could do to comply with at least Tier 2 requirements for the Clean Air Act in California, and hopefully do better than that. The building had great bones, and with that group of people working together, we were able to come up with a facility, I think, that met all of our expectations, and in fact, got us a little bit of notoriety in the press. So it was good. So what does that mean to customers? It means that we can go to the customers and we can say, we have a facility that is capable of producing an environment that can deliver 200 watts a square foot. We are going to enforce, once you come into that facility, good practices within the facility as well, strict use of blanking panels and high-density server configurations, strict use of hot and cold aisles to make sure that we're not mixing hot air with cold air and wasting the cooling that is so precious in a facility like ours. And I think that with that group working together, we have produced a pretty good cutting-edge facility. And I hope that answers the question, but that's how we really have to go about designing the sites. It has to be a cooperation between the utilities, the city, and the manufacturers, as well as the data center operator, to make sure that we deliver that infrastructure.
So that was what you did as far as the building is concerned. What happened when the first customer walked in? Brand new servers or maybe a couple of years old?
In the particular case of Milpitas, everybody who's coming in there is a fairly new company with a lot of brand new equipment. I have not seen myself anything that I would consider legacy hardware going into that facility.
Oh boy, the word legacy. Sorry. Yeah, two other people I want to talk here, either Chris or Edmund. Do you want to talk about legacy customers and what you can do to motivate them into this new utopia of higher quality colo and better use of power?
Well, the simple answer is charge more, I guess.
Tell us more.
Power rates are going up, so.
Can't hear you.
I said power rates are going up in terms of, almost every market. So the way to, obviously encourage people to go green with the equipment that they bring into the data center the easiest is charge them more. They'll use less. Not necessarily the smartest business move, but from an environmental factor, I would go back to Josh's point. When you're trying to, you have a 100 megawatt data center, trying to do anything that generates that much power, environmentally friendly, in a high density area is going to be really difficult. So obviously the only thing that we can do is, besides smaller green initiatives within the company, is encourage the customers that come in to use more efficient things and through power rates, encourage them to replace the equipment that might be less efficient with more efficient equipment as they move forward.
Is it working?
I don't know. I don't have an answer to that.
Okay, Edmund, grab a mic. Tell us a little bit about what you're doing.
Okay, well, let me just say that I'm sitting in for Equinix. I am a consulting engineer, so I've been exposed to not just Equinix data centers, co-location facilities, or as they call it, IBX, Internet Business Exchange facilities, but I've also seen other types of data center that you would consider as enterprise data centers, telecommunication data centers, different types of data centers. And I can tell you that when you build a data center, one of the first things that you have to make sure is that there is power. Okay, you don't go into a particular area where power is not available from the utility, or the utility does not want to deliver that kind of power at that point in time. That is a very, very important step, doing your due diligence. Now, let's say that everything is hunky-dory, everything, power is there. Next thing you need to do is make sure that you can put the number of generators to back up your power, because that could be your limiting factor. Utility can pump as much MVA or amps to your facility, but if the local jurisdiction does not allow you to put that many generators to back it up, you can't sell that power to your customer. You have to make sure that your power is backed up. Let's say you have enough generator capacity to back up the power that you're going to deliver. Now comes the communication between the salespeople that are going to these customers, end users, that they have X amount of power. They need to talk to their facilities people. They need to communicate so that they don't, overcommit the power that's available in that data center, power and cooling. So that's very, very important. And the way, the way we do it, or the way Equinix does it, is that they have a very good way of communicating between their salespeople and their facilities people. Also, they employ monitoring system so that they're able to monitor down to the branch circuit level, going to the different racks, going to the different receptacles within the rack. That way, if they're about to exceed their allotted power, then they would get a notification. Or if they inadvertently cause a short circuit and they go down, Equinix or the facilities people would know what exactly happened. So there are many ways of approaching and making sure that continuous power and reliable power is delivered to the customer. That's very, very important. There are, I think everybody have talked about it throughout this whole convention. I think there was a lot of things that were mentioned about how to make a data center more efficient, free cooling, which isn't really free. You use the term free, but it's not really free because you still have to pay for running the fans, the air handling units, everything. You gotta add the extra piping and valves and all that. And I think some of the people that have done their presentation before have touched on the two types of free cooling, and that is the air side free cooling and the water side free cooling. Of course, water is probably the best solution. So those kind of things are being looked at. We're also looking at UPS system, making sure that they're efficient. You've got, two types, well, you got several types of UPS system, but the two types of static UPS is the SCR type and the IGBT type. IGBT UPS is predominantly used because of the efficiency, on a wider range. In other words, you could operate an IGBT type UPS system half its load, and you'd still be up in the 90s, 92, 93% efficiency. If you operated at 100%, actually your efficiency drops. Your best bet is 75% load, because they design them, because most data centers do not operate their UPS at 100%. They operate right around 75%. So they aim for that, for the highest efficiency. That you will get about 94% in some cases. So little things like that. We use occupancy sensors. Okay, and that way we don't have to burn power that we don't need. But when you design a facility, you can't design it for the lowest efficiency. You have to design it for the worst case scenario. That is a very important thing to remember. Let's say that our efficiency is 90%, or I shouldn't say that, but let's say that our overall PUE, which stands for Power Utilization Effectiveness. Everybody was talking about 1.53. I think somebody addressed, EYP did a study and they found it was 1.53. We're seeing higher than that. It depends on the design, the configuration of the system. And it's mostly on the mechanical side, by the way. You have different types of mechanical system. You have the water-cooled system. You have the chilled water system, which is pretty common. And then you have the air-cooled condenser, DX system, okay? And then you have the absorption-type chillers, okay? You have many different ways of designing a mechanical system, and your efficiency is going to be determined by the type of mechanical system that you use. What type of mechanical system you're going to use depends on your usage. So these are the kind of things that, is part of that same equation that would determine your overall efficiency. So to say that it's 1.53, you need to qualify that, okay? That might be your efficiency on a good day, okay? But in reality, it's going to be a lot higher than that, okay? That's just the way it is in reality.
So I'm going to lead off of that. We've heard from everybody here, and we've talked about efficiency of the chip, efficiency of the system on the server side. We didn't have switch and router guys up here on purpose because we did that 2 years ago, and we thought it was really time to look at the server side of it. We talked about the data centers and from an engineering standpoint, how efficient that can be, and all that's great, and that's as green as we can be inside the colo. But that's as efficient as we can go. It's maximizing use of space, systems, all the way down the line. But now we're outside of the colo, and we actually have to generate electricity to actually feed these facilities. So it falls back on guys like PG&E or other utilities. So I actually need the audience to pay attention on this one because I need to raise a hand. If I were to tell you that if I provided green power to that data center, now I can't actually say that exact little bit of electricity coming in my line is really produced from that windmill, thousands of miles away. But we dye the electrons, yeah, so now we all know. But let's just say I go to the utility and I'm paying 10 cents a kilowatt hour for normal electricity, but if I can get green electricity and have that guaranteed for a set period of time, I'm paying 15 cents a kilowatt hour. I, as a data center operator, and nobody else as a data center operator is going to absorb that. So by a raise of hands, if I were to sell you green power, would you pay, say, a third more to your provider, like Terramark, CRG, Switch and Data, Equinix, to provide you green power? Raise of hands. Now, what does everybody think about that? So all of us, who's driving a Prius? Oh, we're really bad geeks. Bad geeks. So here comes the situation that we all want to be efficient, we want to be green, but nobody wants to pay for it. So in the end, where do we end up? I actually moved from Florida. I live in Austin now. Austin Energy is a really cool city utility, and they have a lot of green power. They'll guarantee an internet exchange or data center provider green power rate higher than a normal rate, but they'll guarantee that rate for 20 years with no inflation. So that means that in about 4.5 years or so, roughly just giving inflation, you'll equalize what you'd have for normal energy rates. Now, of course, cost of fuels are going up, so in the end, you'll probably be ahead of the game. But the question is, who's going to pay for that in the first 4.5 years? Nobody wants to eat that, and they're probably going to charge more to a customer who actually provides it. So I thought that was interesting. But I want to lead over to Mark and see what he thinks about that, and maybe if they're talking about in the future, to put him on the spot of bringing their green energy rates into the same line as their regular energy rates, so that we as data center operators can provide you green power.
So in some ways, I'm not the best person from the utility perspective to talk to you about this. Half of the generation that I deliver to my customers comes from hydro. We don't count that as renewable, and we don't count that as green. I have a regulatory mandate that by 2010, 20% of the power I deliver to my customers be renewable, and we're at 18-something, and frantically trying to buy into thermal electric power plants down in the desert and other renewable sources outside of California because we can't generate enough here. So you're going to pay for green power whether you like it or not, because I think the regulatory community is going to tell your utility to do it. And coal is no longer going to be king, and your rates are going to go up. I would just point out a couple of quick hits on some of the things. You know, cheap power in the Pacific Northwest at 3 cents a kilowatt hour, that's based on existing underutilized utility assets. And as soon as those utility assets get back up to full use again, because the smelters left the Pacific Northwest, once they get back up, that power is going to be expensive. They're going to see rate shocks that I don't think you're going to see here in California. We're already pretty expensive. There's a lot of talk of, well, if you want 10 megawatts from the utility, you can't get it. And I will stand up on the behalf of the utility industry and say, I'll get you 10 megawatts anywhere you want. Just bring a big, big checkbook and bring a calendar that goes out a couple of years. There are reasons where we don't want you to build your data center. I have 5 circuits in downtown San Francisco that are maxed. That means if you want more power and you're on that circuit, I've got to upgrade the substation. I've got to upgrade the transmission system that serves those substations. I don't want you expanding there. And I've got some existing data centers that were part of your Google tour who want more power. Not the right place. I've got places where I can accommodate it, but I've got places where it's really difficult for a utility to do that. The last thing I'll just give you, liquid cooling inside the data centers may certainly be a technology that gets you around some of the things, but somebody sent me 2 photos last week, and I wish I had them here, the kind of liquid cooling that you all need to avoid. It was a photo of some IT guys who had set up garden hoses, hoses, shooting water onto the utility distribution transformer outside of their data center to keep it cool. I'm a mechanical engineer, and I know enough about electricity not to stand around that kind of liquid cooling solution, so, and I'll leave it at that.
All right, and guys, we're actually going to open up to questions. So, Randy, come on up here. Hurry up.
Okay, if you're asking questions, name, affiliation, and total amount of megawatts you're responsible for.
Name's Anton Capella. Affiliation is 5nines Data, the smallest colo on the internet, and we use exactly 0.3 megawatts. How's that? Not even one. So one observation I made during Josh's tour was all of the buildings had good aerial shots and such. They had just wonderful resolution, but I couldn't quite see the details. But I think what I saw was none of them had any solar shields. Is there any particular reason that's not seen as beneficial? Is black body not a significant source of heat load you eventually have to remove in addition to the load from your servers?
Yeah, that is the weirdest question I've ever heard.
I mean,
I love you, Tony,
never
but
know.
so let's take, I'll do it from my building perspective. I've got a 120,000 square foot roof plate, That's number one. I have 3 giant 16-meter satellite dishes, or 2 16 meters and 11-meter dish surrounded by these giant balls on the roof. And then how am I going to put something on top of that that's going to be a solar shield, not solar panel, solar shield like you said, that isn't going to blow away in a 200-mile-an-hour wind? Anybody want to stand around that when the wind blows? So that's just Miami. Chicago, it still gets windy. It's still an issue. I don't know. I don't think the solar heat load on the actual roof of the building is much of an issue. Or are you talking about the skin?
It's the entire thing, right?
Yeah. So green screening it or something is what you're trying to say. So you get a.
That's a great color.
Yeah.
So the answer is people are doing it, but they're not doing it in the type of data centers that Josh is running. If you take a very, the example one I'm going to give you is 200,000 square foot in Sacramento, California. The data center is run by Raging Wire, which is a well-known company, and they took the top of their roof that had no HVAC or any other equipment on it whatsoever, so it was about as clean as can be, put a white polymer coating on it, dropped the inside temperature on now I'm doing this off memory, 32-foot clear height data center, and dropped the inside temperature of that roof by just about 20 degrees. That does make a difference.
Absolutely. So
Payback, which is more important, 9 to 10 months.
we should all be doing it, right?
Sorry. They didn't do it by their own choice. They had a state standard. Okay, so that's why they did it, but they made a good PR piece out of it. So
Sure. So we're talking about maybe even if it's a small % margin, it's a big improvement when you're removing 10 megawatts of heat, right? We all would recognize that. So
yeah, it made a difference. That the payback is the reduced utility bill.
So it's not a sexy technical solution. There's no moving parts. I mean, it's not cool, but it
It's
certainly
some
seems
white,
like a relevant
white
thing.
polymer paint.
Sure.
That's all it was.
Sure. So
On a roof that could do it.
Tony,
That's great.
Okay.
I mean, the other problem is, you know, I mean, for all those buildings that you were looking at when Josh was touring around, most of them had, you know, a large amount of heating, ventilation stuff and generators on top, plus, you know, roof rights for communication equipment. I mean, when you start putting a whole bunch of antennas up there, generators, air exchangers, I mean, you're gonna run out an efficient way to put a solar shield over the building.
Sure. So go ahead.
So one other quick comment is that I don't know if you've looked at the output of photovoltaic arrays lately, but you know, typically at high noon, incident sunlight on the Earth's surface on a clear cloudless day is about 1 kilowatt per square meter. The efficiency of most solar panels is around 15%, maybe 20, 30%, really good expensive ones. You will get about maybe 150 watts out of a square meter of solar PVA. And even if you took a 100,000 square foot data center and somehow you were able to cover the entire roof of the 100,000 square foot data center with 20% efficient PVAs, the max you could generate out of that is 2 megawatts on a clear cloudless day, and of course you'd have a problem at night.
Oh, I wouldn't hope that you thought I was suggesting you should cover your roofs with solar cells. PVs, as you mentioned, are not the greatest. I think it's probably more expeditious to remove the energy in reflectivity than ever try to absorb it and use it, right? I mean, that's my point. It seems like it'd be possible, if you're thinking about it, to build a new facility. Sears Tower, for example, has tons of antennas on the rooftop, but many more inside units, inside windows. So co-locations of radio facilities, very reasonably easy to, I think, work around. Anyway, that's just the point I want to launch to you guys. Thanks.
Owen DeLong, Jitter Networks, and I'm probably responsible for about 0.01 megawatts. But the point I wanted to make, since I was one of the few Prius drivers that raised his hands in response to your question, is I didn't buy the Prius to be green. I bought the Prius because my LX470 was consuming $700 a month in gasoline, and the payments on the Prius were a little over $500 a month, and it used $130 a month worth of gasoline. So when you add those together, you get $630 versus $700 plus a month in gasoline that I was using, and suddenly you realize that I'm driving the Prius because the Prius was free.
And you probably get to drive on the diamond lane. Nope.
So
I have a question about server form factor. It seems like we were all sort of rushing towards higher and higher density in servers a few years ago, and now we don't seem to be anymore because I guess the power shortage in most data centers has taken that pressure off. But it seems like high density and making things small is its own value. It seems like making servers smaller means that there's less manufacturing that goes into them. If you're trying to make things green, you know, when I was buying Sun servers 2 years ago, 16 servers fit in 3U. The smallest Sun servers now, 10 servers fit in 10U. And that, as a blade chassis, that doesn't seem to be wildly more efficient than just stacking up 1Us. So I'm curious what happened to the trend to making servers smaller and more space efficient.
The trend continues, and for example, at our engineering compute centers at Intel, where they actually model the semiconductor and the chip, you know, we're very high density with all blade chassis, 64 servers, 64 dual processor quad core servers in a rack, you know, roughly 30 kilowatts.
64 in 44U, though, is really, really bad compared to where we were just 2 years ago.
Well, but I mean, it's I'm not sure why it's that bad compared to where we were 2 years ago. What do you mean by that?
Well, because if we were at, let's see, a Sun B1600 chassis, right, 16 blades in 3U, each blade dual core, right? That's a lot higher density than slightly over one server per U. I mean, we seem to have fallen back to basically one server per U.
Well, but
I'm not sure why.
Well, for one thing, you have to consider cooling. How are you going to cool if you get much beyond these 30 kilowatt racks? Then you have to start spending additional money.
I'm not talking about filling whole racks with these. I'm saying that if what you want is, say, 16 servers, why 2 years ago could I get that in a 3U package and now I get it in a quarter rack? That's a step backwards.
So let me try and address that. So I know exactly which product you're talking about because that came out of my division at Sun. And you know, one of the things you ought to bear in mind is that it's not just the server vendors design the server for a number of things. They design them for, in some cases, performance, in some cases, performance per watt, in some cases, you know, reliability, availability. They put dual redundant everything. If you're going to run a mission critical database or something on it, you know, you don't care about energy efficiency in those types of machines. Typical mid-range machines, you care about dual redundant disks, dual redundant power supplies, dual redundant everything. And also what's happened is that the nature of the applications that people run has changed. And, you know, in that particular form factor where you had a single blade about, you know, basically 4 inches high.
That would fit in a FedEx envelope,
that
by
would
the
fit
way.
in a FedEx envelope, exactly. That was actually, I believe that was probably still the smallest server ever built in the industry. But it's really hard to get 16 gigabytes of DRAM, for example, in that form factor. Or, you know, the new class of CPUs that are coming out that are dual core, quad core, you know, 70 watts, 80, you know, 70 to 150 watts, etc. Memory DIMMs also generate a lot of heat. In fact, most of the servers that we make, the amount of heat that's produced by memory actually dwarfs the amount of heat that's produced by the CPUs. And so to get any reasonable application workloads that need a reasonable amount of memory, maybe some disk, I think the machines you were referring to were diskless blades. And certainly, you know, there are people that want disk-full blades and so on and so forth. So really the trend towards optimizing for performance per watt hasn't changed, and that's improving. The servers will get, in some cases, somewhat physically bigger, but they will get better, certainly in performance per watt. It also turns out that the more you enclose all sources of heat in a single chassis or a single cabinet, the easier it is from a cooling efficiency perspective to cool them, because they're not just, it's not just a bunch of one-use servers that are sucking in air from the front individually, 40 of them in a rack, and exhausting air individually outside into the hot aisle. They are now, the cooling is now much more integrally designed. The heat sinks are connected, they're networked, people are looking at liquid cooling coming directly into the server racks and server cabinets. It's a lot more efficient to do that if you design for high density.
The one other comment about form factor I would make is if you go look at the Sun container and count the number of fans in there and determine how much fan power is being used in that, then go look how many fans and how much fan power would be used if you had that many servers all 1U, in racks, right? So the efficiency with some of the new form factors coming out in terms of reducing fan power, better application of power supplies is helping the performance per
I'm
watt.
all for blade chassis. I'm not arguing against blade chassis. I'm arguing for blade chassis. I'm arguing for making them smaller than they are right now.
So, Michael, can you just tell us, so in a classic 1U or 2U chassis, how much power is being used by the fans?
It varies by manufacturer, but we've been talking about this, and it could be roughly 40 watts in some of our platforms when they're ramped up at top speed. I've seen reports in a 2U that you could get up to 100 watts of fan power in a chassis.
It's a lot of power just on the fans. All right, let's... Okay, so no, that's a very good question, because I didn't ask Michael the other question. So a classic 1U or 2U, and in your case, let's say a dual CPU Intel solution, how many watts does an average 1U or 2U server take?
Well, again, we'd have to look at what's inside of it, right? I mean,
sure.
But we're looking at. I was looking at some trend data just earlier in the weekend. We've got some well-monitored servers, in the energy or in the engineering compute, and they're drawing actually about 250 to 300 watts per.
So if I do simple
dual
math,
processor.
right. So
server.
let's say 300 watts for a 1U server and 30 watts for the fans. That's 10%.
Yeah.
How much Josh? How much do you spend on electricity a year?
Millions. Just leave it at millions. A lot
So
of money.
10% of millions is it makes a difference?
But it's not 10% of millions, because what happens, there's a power supply, right? And if it's a climate savers and you're at 90%, that's great. But if you're at 70%, 80%, you've got that inefficiency. Then you've got the inefficiency of the power distribution from the utility coming in, and then you have to
cool it.
You have to cool it.
Okay, so
I mean, all that.
it isn't insignificant, I think, is the point that's being made here. It is small, but it's not insignificant,
Not
and
at
it
all.
really does convert to real dollars. Let's go to...
Hi, Brian Dixon, Affiliates. A very small amount of power responsible for, probably 0.01 or less kilowatts. The whole system, if you look at where there are other places, would be including transmission systems, power transmission, and the kind of power that's being used for power supplies. So AC versus DC, and going off grid, avoiding the 30% loss in power transmission. Any thoughts to the kinds of off-grid solutions that allow you to avoid even having the backup systems in place, such as going nuclear? That allows for a lot of growth long-term and avoids that 30%, and going to all DC rather than AC for the servers and the distribution systems.
So I want to speak to that from I'm going to start out with DC power first. So when a router or switch guy comes in and installs big DC power into some of their big hardware, or say big bulk feeds from 777 cabling into a 400 amp feed into a BDFB, and they distribute it from there, I feel okay. We as the provider, the colo, drop off that into the BDFB and tie it down, and they distribute it inside their cage and deal with that, or we do. When you get a server guy coming in and trying to deal with DC, I'm terrified. Now, it's great because it is easier, there is cooling benefits, there's no question, but I have to all of a sudden start worrying about voltage drop issues that are really get obscene when you start dealing with the server environment, because it's not a bunch of bulk feeds, it's a bunch of small cabling. We also, but I'll step off to other power too. 120 we hate, 208 we like a lot more. It's easier to cool. So there are a lot of issues that play around with that, and that again we end up relying on the vendors as a carrier neutral colo. Tom has a different story here with Amazon. He can choose 50,000 servers across a data center that are the exact same thing. Well, you can get really efficient that way. But when I've got 1,000 servers here, a bunch of CRS1s, 500 servers there, all different vendors, all different fan stuff, different everything, it gets really difficult. But do you want to talk about the 30% drop? Yeah. I know, and he was bouncing over.
Actually, I just want to insert a scheduling thing. We have actually hit 4 o'clock. I don't want to interrupt the conversation, but I did want to let people know that we do have a half-hour break starting now. So feel free to stay and listen and ask questions, or grab your break.
Trying to take it? Yeah, so yeah, there seems to be this rumor that there are huge losses in utility distribution and transmission systems. There's huge losses when I put 10 units of fossil fuel-based energy into a power plant. I get about 4 out. That's a huge loss. But I've got hydro, I've got sun, I've got wind, I've got a lot of other systems that are generating my power. So if you're pointing out the loss in a fossil fuel power plant, I agree. Transmission, 4%, folks. I move power around interstate, and our transmission losses are 4%. I can move power down here from the Pacific Northwest maybe at 5 or 6% losses, not 30%. Never has been, never will be. Thank you.
So, I wanted to comment on DC-powered servers, if that's okay. And then,
yeah.
Lawrence Berkeley National Lab just recently completed a demonstration project, which we were happy to be part of. And when you look at that, it talks about the benefit of DC-powered servers. Interesting in there, it showed that you could get sorry, I guess I'm not supposed to use this word, but from a legacy design, you could get a 28% improvement by going to DC power, okay? But what else was very, very interesting is if you go back and reread the report, you can actually get a 23% improvement from legacy to just using high efficiency standard design stuff, right? I mean, what everybody's used to, the 208 volt power, is that you can get a 23% improvement over the legacy power. So the point is, look at DC power, look at the 400 volt AC power as an option, look at standard power as an option, but in any case, make sure you get the high efficiency components from the utility right to the server.
John, go ahead.
Yeah, I was just going to say 2 quick things. First, even if you're using DC power, remember there's still a rectifier in between your AC feed and distributing it on a BDFB, so you're going to get the loss. It's just a matter of whether it's on the server or whether it's through the rectifiers. And the second thing is that when we design data centers, and like the NAP is one example, and other examples that we can look at, the higher the voltage, the easier the distribution. If you've got a very large data center and you're taking feed from the utility, generally they deliver it at 34.5 or 34,500 volts, and then through a large building we'll carry it at 4160 and break it down when we have to. We don't usually go 480 unless we're in very close proximity to where we're actually going to put that into a UPS or into a transformer. So we do try to maintain within the data center enough efficiency within the voltage and within the transmission that we don't lose any power.
Tom?
Yeah, I want to thank Josh for all the nice pictures of railroads. In 1960, Theodore Levitt had said that the railroads failed because they thought that they were in the railroad business rather than the transportation business. We've heard an awful lot about the data center business here, but the one thing that all of us content producers and ISPs and so on share is we're in the computing business, and we've talked not at all about managing variance. We've just talked about building to peak, and a huge amount of the computing, whether we generate it ourselves or whether it's in colos that we run, is not really needed this next 2 seconds. And so if people have ideas about how to deal with that in order to get greater efficiency, it'd be nice to hear a little bit about that. By the way, too many megawatts to mention.
I mean, I think that the virtualization people and some other bright lights here in the Valley are working on that problem, which is, okay, I virtualized, I went from 1,000 servers down to 200, but I'm still sized for double my average load. And they want to be able to shut those servers off with the confidence that you need that they'll come back on when the loading comes back up. So I think that's sort of virtualization 2.0, if you will.
And Tom, real quick, we specifically, Martin and I were debating what to do on this panel, and we specifically kept virtualization out of it. We know it's hot right now, but we wanted to get to these tough points, and then at our really, we're going to run another panel here coming up again, and we'll start going into efficiencies for virtualization, chipset designs that get even deeper, more liquid cooling, stuff like that.
I think, Josh, what I'm thinking about is more not how you slice up the servers, which virtualization helps you with, but rather how you shift load, which running your dishwasher at nighttime rather than during the day helps with.
So well, you're shifting load within a data center, so actually dealing with data center switching and how you handle big loads like that, that is definitely a big topic we need to cover as well. I agree.
And at the other end, I've got some data centers thinking about thermal energy storage now. As, let's build the chilled water at night when it's cheaper.
Services. We use maybe a quarter of a megawatt. I wanted to kind of talk about the fan issue because really now you're getting down into the micro design. And when you consider the fan, you've got a wafer that's maybe 2 centimeters square that's generating most of the heat in a server. And you need to move that heat out of the server. And the most efficient way to do that is might be with some type of a pipe, liquid pipe that like you see on some of the laptops, but eventually you're going to have a fan to get it out of the box. And so what you wind up with is the server designer just wants to get that heat away from the chip. And when you start stacking these things up in a rack, depending if you get different brands of servers and they don't think on a larger scale to move all of this hot air move all this heat in a particular direction, you now have hot air mixing with cold air and what have you. Even designed to the rack, is it going into a 2-post rack, is it going into a 4-post rack, what's the airflow in the facility? So I think really in order to address the fan issue in a realistic manner, you've got to get the server designers to come up with a uniform way of, okay, we're going to take cold air in here and push it out here. And I don't see any industry-wide thing with the different server manufacturers doing that as they go on. Some devices move it side to side, some front to back, and what have you. So I think that's something that from an industry standpoint, if the various makers of this gear could get together and work with the HVAC people and everybody else to come up with a uniform specification of this is the way we're going to move the heat within a rack.
We only have 5 minutes left because we are digging into the break, so we're just going to take comments really from everybody, more than questions if we can, and I'll try and answer them as quick as we can because we are definitely over time now. You were waiting a little longer, so.
All right, my name is Gilbert Gong from Box.net, very small power usage. I just wanted to comment on your question about if the pricing for power was going to go up 50% for green power if we'd pay. And I think part of the hesitation there is that when colos are charging against the breaker amp and not the usage, and there's a difference between passing through the cost. PG&E, we know as a regulated utility, has to charge us similar to how much it actually costs them. I think if it was clear that the amount we were paying was actually the differential that is being paid to the utility, we probably would be a lot more willing to pay that differential.
So that comes into my presentation earlier in the model war. And in the end, it's business. So one model will win out over the other, or they'll equalize or not. And that's something I think is going to play itself out pretty well.
Robert Enger, Narrow Step. During the initial overview, attention was paid to those co-location centers that were adjacent to transmission substations, and in some cases adjacent to communications rights of way. There wasn't any mention of colo centers that were located adjacent to industries that could make use of the waste heat.
Yeah.
Pretty low-grade waste heat by an engineer's. I mean, you could put greenhouses around them. They do that around nuclear power plants in France.
Well, let me just say that that is not a bad idea, but how many places like that are there? Have you ever heard of bagasse? Bagasse is a way of generating electricity from sugarcane pulp. Okay, instead of throwing away, hauling it to some landfill, they would pulverize it, they would burn it, and make steam to generate electricity. The Department of Energy has done many studies on that. In fact, there's a study that I read where they can actually provide power for the sugar mill and for the whole town around it. So if you have a data center next to a bagasse facility, that would work. But how many of those places do we have around here? So that's probably the problem.
Actually, I have something to say to that. I used to work for the cogen in New Jersey, and New Jersey has a lot of landfills. And we were able to produce enough electricity from a small landfill for 30,000 homes. And so it's being done. And it's very efficient, cleans up the green air. I mean, no methane, so it's better for the environment. And it was very efficient. And so, we have enough, landfills around the country. We really could do that. We're building next to railroad tracks, other stuff. It's a really good thing to think about for the future.
Yeah. So I'm going to wrap it, but I'm going to give you, if you want to follow up on that one, go look at two different companies that can help in this area. Native Energy, easy to find in any search engine, and TerraPass is another company. You can look at carbon offset purchases, you can look at RECs, renewable energy credits. If you look at Native Energy, you can go find some biomass projects. We've got to wrap it. Thank you for everybody for staying. Couple of housekeeping comments before I thank everybody. I got to thank the panelists and the companies that let them come here. Thank you very much. Remind you, you've got only about 25 more minutes. If you've got a lightning talk you want to get in this afternoon, get it in now. You've got 25 minutes. And the break, thank you to Force 10 this morning and the London Internet Exchange links this afternoon. Thank you very much, everybody.